Okay, let's dive in. Picture this. You're dealing with core samples, seismic surveys, satellite imagery, drilling logs. I mean, it's not just terabytes, it's potentially petabytes of information.
Yeah.
All tied to specific spots on or, in the Earth's at particular times.
Right.
In geosciences, just collecting this data is hard enough. But the real Everest,
Yeah.
actually managing it effectively.
Absolutely. And it's not static, is it? Geological data is often, it's multidimensional. It evolves over time.
Yeah.
And its ultimate value really rests entirely on how well you can organize it, access it, and, understand it years, even decades down the line.
And that's precisely what we're unpacking today. We've been
Yeah.
digging into a really insightful article from Alqubalee Notes titled Management of Geological Data, Local and Cloud-Based. Got a fresh update just recently, May 29th, 2025.
Yeah, so our goal with this deep dive is basically to pull out the core insights from this piece. We want to show you why geological data management is such a critical challenge, kind of unique to this field, and then walk through the two main approaches the article explores, keeping your data close, local repositories, or using the power of the cloud.
Right, so let's start with the fundamental why. The article makes a pretty strong case. Effective data management is just, it's non-negotiable. Essential for accuracy, accessibility, usability, especially as these data sets just explode in size.
And what's particularly highlighted here, which is really key in geosciences, is the absolute necessity of managing the metadata right alongside the raw data. This isn't just technical jargon. It's the vital context. Where did the sample come from? How was the seismic shot? What processing steps were applied? Without that, honestly, a vast data set is just noise.
So the metadata is kind of the story that makes the numbers make sense.
Precisely. That's a good way to put it. And documenting the lineage of that data, how it was acquired, processed, interpreted, is explicitly called out as critical for ensuring data quality. You really need that transparency.
The article also touches on needing an interactive component, suggesting it's not just about static storage, but dynamic control over the data.
Yeah.
That implies tools for visualization, querying, maybe even real-time processing capability.
It does. And when you tie all of this together, the raw data, the detailed metadata, good process documentation, and that ability to interact dynamically, you basically build a framework that boosts data integrity, makes collaboration way more efficient, and fundamentally improves the decisions you can make based on that data. It's really the groundwork for unlocking geological potential.
Okay, that sets the stage nicely on the why. This is also important. Now for the how. The article spends a good chunk of time on web-based systems, which, often means cloud repositories. What are the big upsides there?
Well, the most obvious one, and arguably the most impactful, is accessibility. Simple as that. With web-based systems, you can access your data from pretty much anywhere with an internet connection.
Right.
For international research teams or, say, field crews in remote spots needing reference data or to upload new findings, this is transformative.
Yeah, that geographic flexibility seems huge, doesn't it? Especially for collaboration.
Absolutely. And beyond that, these systems are generally built to handle truly massive data sets without requiring you to constantly scale your own physical infrastructure.
Yeah.
The cloud providers manage the hardware, which frees up resources.
Makes sense.
Plus, many platforms are now designed with user experience in mind, offering more intuitive interfaces and integrated tools for working with complex, multidimensional geoscience data. That helps streamline workflows.
And the article provides some excellent practical examples, right, of large-scale, public, web-based geological data systems already out there.
It does.
We're talking about national efforts like the USGS Data Management System, the Geoscience Australia portal, the British Geological Survey's data section, and the National Geological Database of the Saudi Geological Survey. These are massive public resources.
They really are. But it also points to broader research infrastructure platforms that host geological data, too. Registries like re3data.org and DataSite Commons, they catalog numerous cloud-based repositories across different disciplines, including dedicated geoscience ones.
And for researchers specifically looking to, say, publish data linked directly to their papers, it mentions platforms like Open Science Frameworks and Zenodo as useful cloud options.
Yes, exactly. Those are highlighted specifically for providing persistent identifiers, or DOIs, for datasets that makes them easily citable and discoverable right alongside the article they support.
Okay.
And they offer specific storage tiers. Open Science Frameworks is around, 5 GB per project, and Zenodo offers up to 50 GB per upload, which is pretty generous.
So that covers the cloud side with its emphasis on accessibility and scalability. But the article is clear. This isn't necessarily a one-size-fits-all solution. It contrasts this approach with deploying a local data repository. What are the distinct benefits of keeping data, on your own infrastructure?
Control. That's probably the core advantage. Control and security. When your data lives locally within your own network, on your own hardware, you retain a much higher degree of control over access, management, and especially security.
Right.
And that's just non-negotiable for many organizations, especially those dealing with highly sensitive or proprietary data, like, say, exploration results.
So for things like intellectual property or maybe nationally strategic data, local kind of feels like the default just for security reasons.
Often, yeah. It reduces reliance on external providers and, well, it mitigates risks associated with third-party infrastructure. Local systems can also offer performance advantages sometimes, especially for very large files or really complex queries that might get hampered by network latency in a cloud environment. Plus, you generally have more flexibility for deep customization to meet very specific organizational needs and integrate with existing internal systems you might already have.
And crucially, the article points out offline access. Being able to get critical information without an internet connection. That seems like a huge benefit, particularly for field operations in remote areas where connectivity is, let's face it, often unreliable or just non-existent.
Which, as you know, is a very real scenario in geosciences.
Definitely. And the article also lists examples of open source platforms you could actually use to build and manage your own local repository, giving you that control. Things like InVNRDM, GKHub, Harvard Dataverse, and OneGeology. These provide the software foundation for organizations to create their own secure, controlled environment.
So we've walked through the landscape then. Why managing this complex data is so vital, the distinct advantages and examples of web or cloud-based approaches, emphasizing accessibility and scale. And then the benefits and platforms for local repositories, which prioritize control and security. Ultimately, as the article concludes, the choice between local and cloud, or maybe even some kind of hybrid approach, it isn't trivial. It's actually a strategic decision. It demands a thorough understanding of the strengths, the challenges of each, aligned with your specific data types, security needs, collaboration requirements, and, well, the resources of your organization.
Yeah.
It's really about choosing the path that best lets you extract value from your geological assets.
And here's the sort of forward-looking thought the article leaves us with. It states that as technology continues to evolve, and it's evolving rapidly, staying informed about emerging trends is crucial, not just for refining existing data management practices, but for enabling more innovative and effective uses of the data itself.
Yeah, which raises a really fundamental question for anyone in this field, I think. Considering how quickly technology is advancing, think about AI for analysis, new visualization techniques, edge computing. What does truly staying informed actually look like in practice, especially for managing critical geological data over the long term?
It's not just keeping up with new storage tech, is it? It feels like it's more about anticipating how future tools might change the way we interact with, analyze, and derive insights from this data, maybe ways we can't even fully envision today. Definitely something for you to consider as you navigate your own data challenges.